Okay, so derive an equation for the capacitance of a spherical capacitor in terms of the given variables and physical constants, and hopefully we can do it in terms of all these variables here. This is like a cross section of like a spherical capacitor. So usually a capacitor is like two conductors that are like a separate distance away, and they store charge. So in this case, we have a sphere, a conductive sphere. We can think of it as a shell of a sphere, and then we have another sphere, kind of once again hollow on the inside. And yeah, they're in two conductors a distance away, and we can figure out the capacitance. Well, how do you figure out the capacitance? The capacitance is I haven't made a video on this, but if you understand capacitance, you should know that capacitance is the ratio between the amount of charge stored on that capacitor over the electric potential difference, the voltage between the two capacitors. So we know Q, because hey, that's the amount of charge on each capacitor. There's the same amount of charge. How do we figure out the electric potential between them? Well, one way we could do it is we know that not the electric potential, the electric potential difference. One way we could do that is we know that, hey, electric potential, I'm saying way too fast. The electric potential difference, the voltage is equal to the electric field times the distance between them. So you might be tempted to say, hey, let's just use this equation. Well, that only works if the electric field is constant in between them, right? Like a parallel plate. This works great for a parallel plate because the parallel plate has a constant electric field. Not so great for a sphere where the electric field gets weaker as you go out. And remember, inside a hollow sphere with a net charge, which has like a charge, excess charge or whatever, the electric field is zero. So the inside of here, inside this like air or vacuum, whatever, inside of here, this outer shell is not causing an electric field inside. So if we want to find the electric potential difference inside of the sphere, you got to focus on this sphere. This is the sphere that is going to cause that electric field, that's going to cause that electric potential, essentially. So it's not constant, so we got to do an integral. So if I were to say V, the voltage is equal to the integral of the electric field dr, we'll say, dr meaning distance, and the bounds we're working with, we're thinking, well, so the electric potential, so this is, we'll say RB, this we'll say is RA, just switching it around. So we're doing our bounds from the lower RA all the way up until RB. Okay, what is the electric field caused by this sphere? Well, it is going to equal just, and you can use Gauss's law to kind of prove this. It's just KQ1, Q2, sorry, not Q2, just KQ over R squared dr. So, if you were to think about, okay, if you were to think about a dq, and if you were to sum up all that dq and you know the surface charge density and all that sort of stuff, you would end up pulling out the q and the k. So we would get like sort of v is equal to kq integral ra rv 1 over r squared dr. So how do you integrate this? Well, you know, find the antiderivative. So I know r to the, so r to the negative 1. Well, this is r to the negative 2, really. And if you don't know integrals, I haven't taken calculus yet, but this is r to the negative second. So if I want to get, I need to find what function will when I take the derivative, will I get r to the negative second or 1 over r squared? So I know from power rule, if I had a function r to the negative 1, I would take the negative here, and then I would get minus the exponent by 1. You would get r to the negative 2. That's pretty close to r to the negative 2, but I don't want that negative. Right? So I know I'm kind of explaining this fast, but I know people already know this. I would have to put a negative there. That one, when I do the power rule, put the negative one here, it becomes positive. Yay, I get that. So this would be V is going to equal K big Q big Q. Okay, so K. I dropped this. KQ, and then we're going to have, oh my god, 1, so negative 1 over R. So 1 over R would be RB. So we're starting RB, yep. Minus negative 1 over RA. So V is going to equal KQ 1 over RA minus 1 over RB. I can kind of flip these around and be like, okay, this is a negative, minus a negative, that's a positive. So you have negative 1 over RB plus 1 over RA. You can flip those around and get 1 over RA minus 1 over RB, and I'm kind of doing that thing where I draw slanted, but this is our electric potential between the sphere. And I can say V is equal to KQ over RA minus KQ over RB. And I'm going to kind of write here, so I'm not writing slanted. But now, if I wanted to do the fraction math, RB, I'd multiply the bottom by RB, and the top, multiply this by RA, and the bottoms. And I would get V is equal to KQ RB minus RA over RA, RB. That's just some fraction math there. So this is the electric potential difference between the two spheres. And I'm basically done. All I gotta do is plug that into here. This video is about finding the capacitance of a spherical capacitor. It kind of ended up being a voltage video, and that's fine. Because then I just have this. So I can do C is equal to Q over K Q RB minus RA over RB, RA, RB. So if I'm dividing by a fraction, I have to multiply by the reciprocal. So this is going to get on top here. Okay, and then the Q's cancel out. So I get C is equal to, and then, okay, K is equal to 1 over 4 pi epsilon naught. Okay, I'll just write that. So 1 over K, or the constant K, which is what we have 1 over K, is going to equal 4 pi epsilon naught. So I really get 4 pi epsilon naught. So I basically turn that 1 over K into just 4 pi epsilon naught. RA, RB over RB minus RA. So that is the capacitance between, that is the capacitance of a spherical capacitor. Hopefully you notice Q is not in the equation. The charge doesn't matter. And we if you double the amount of charge on the spherical capacitor, guess what? You have double the potential. Everything kind of cancels out.